Okay, recording. All right. So I mentioned in that recap email or announcement last week, that we're going to kind of be skipping around a little bit. So those of you who had lab today and completed EMS, the electronic structure and emission of our atoms, you had kind of basically the bare minimum in chapter, we got through the bare minimum of chapter 6 to get through that. So my goal is so you get the most out of the next lab after EMS, which is next week, is MGE, so molecular geometry. I actually want to skip ahead to chapter 7. Parts of chapter 7, we're going to skip around a little bit just so you're well prepared for lab. It doesn't actually matter what order we do these in. Everything's on midterm 2, so it doesn't matter, again, the order. I will adjust due dates to homework as typical. So I'll make it abundantly clear what is due when. So there are my updates. It's probably not on the recording, but we got through the beginnings of chapter 6, where we investigated light first behaving like a wave. That's why, you know, how many people have taken the E and M part of physics? So the majority of you, or at least half of you. So when we think of light, we think of its wave characteristics, but it doesn't always behave like a wave. Sometimes it behaves like a particle. That's where we call it a photon, a discrete packet of energy that we can count. And so that's where a lot of these, physics memes come from. Just joke about the wave particle duality of both light and electrons. The electrons is kind of the more joked about topic, but I want us through this chapter to be able to understand those jokes, so you can laugh along with the physicists and chemists at those dinner parties. So I don't want you to be alone here. All right, so we looked at the wave characteristics of light. We can associate wavelength with energy. Energy of light meaning that photon packet. That's its particle characteristic, where we have it being quantized. So here's the equation we use to relate the wavelength or the frequency of light to its energy. But the thing is when you use this equation, you are calculating the energy of one photon. Like if I were to throw a ping pong ball at you, that's the energy of just one of those collisions. Oftentimes, when we talk about lasers and energies of lasers, they aren't given in joules per photon. They're typically given in kilojoules per mole because it's just an easier number to read. And so this is a common unit that you'll see in the EMS lab. And I saw some students kind of struggling with this. If if I give you the unit kilojoules per mole, that mole per mole unit there is associated with a mole's worth of photons. So we use this equation, E equals H nu or HC over lambda, to calculate the energy of one photon, but we can scale up to a mole's worth of photons as well. So we can multiply that joule number to increase that energy, typically here given in kilojoules per mole. That's a nicer number to look at. So light is important because we cannot see atoms, we cannot see electrons, but we can see light. And so this is kind of where things get a little hairy. We're looking at light, we're observing light and relating our observations to what that means about an atom. And so that's where we talked about the Bohr model, where this model can correctly explain some of the phenomena we see when we excite atoms. And so we have this electron that can occupy different energy levels. You can think of it as a ladder, but these are discrete energy levels. That electron cannot live in between energy levels. And in order to promote that electron to higher energy levels, we have to give that electron an exact amount of energy equal to that energy difference of those two rungs, of those two energy levels. So the example here, if we go up in, this electron moves up in energy, we have to, the atom has to absorb energy in the form of light. But if the electron falls, energy is being released in the form of a photon. So that is called emission. And so emission and light is involved in our atomic structure picture here when an electron undergoes a transition. That's the big idea here, that when an electron moves between energy levels, light is either absorbed or emitted. Whether it's absorbed or emitted tells us the direction energy is going. Is it going into the system or is it being released? And so there we can do calculations to figure out, okay, what's the wavelength of light being emitted or absorbed? But we can also look at it conceptually, which I like the conceptual part. Relating, okay, these are lights of different wavelengths. They have different energies. They relate to different transitions here. These are all different transitions of different electrons. And so we associated transition A to the photon being emitted with the largest amount of energy, so the shortest wavelength. So the big idea here is like, why does this all matter? Who cares about electrons jumping between rungs of a ladder? This is the reason why we see colors, right? That, you know, visible light is composed of all wavelengths of light between 400 nanometers and 800 nanometers, depending where you are in that region, is a certain color of light. And when a substance absorbs, you know, some region of light within our white light, visible light spectrum, what's reflected is what goes into our detectors, our eyes, and that's what the color we see. So for example, like this black desk, it has energy, electronic transitions equal to that of all visible light, because when light hits it, when white light hits it, everything is absorbed, so nothing, so like no light reflects into our eyes. So we can make you know, relationships here from our observations to the electronic structure of atoms or substances. So the idea is like, why is grass green? It's not because it absorbs green light. It's not because it emits green light, but it absorbs all other colors other than green light, where green light is what is reflected into our eyes. So basically green light, whatever energy that is, there is no transition on grass to promote an electron where energy is absorbed in the green light region. And that's why we see green light. Okay, so, well, let's look at some examples of other substances. Okay, I gotta move a lot of stuff. All right, so grass is green because it absorbs light, right? Absorbs some light, green is reflected. Well, how can we get atoms to emit light? Those who were in lab today did that. Those spectrophotometers that you were using, or those discharge tubes, they glowed, right? You saw light come off out of them. You saw that? You saw that, right? How was that light produced? How was that light? Yeah.
Electricity.
Yes, electricity. Yeah, we had to plug that sucker in, right? So when we plugged it in, we excited those atoms for them to emit light because their electrons were falling back down. So there are other ways we can excite atoms, like using fire. Yes, so we're going to use fire here to excite atoms. So I need to move a lot of stuff because this is kind of dangerous. I have to wear this. All right. Have to wear this. I have to make fire. Someone needs to have this ready. I have my hair tied back. Yeah, you want to? Okay, all right. Okay, there we go. So what I have here, so in lab, you will just see the line spectrum of hydrogen and helium. But the thing is that all elements have their own unique line spectrum. Helium, fun fact, helium was actually when the element helium was discovered. It wasn't discovered on Earth. Its line spectrum was discovered on the sun first before it was actually found on Earth. It's line spectrum, because it looks different from other atoms. Okay, so I have a bunch of different metals here. I don't want you over here, and I need to move my iPad. So we're gonna excite a bunch of different metals and see what they look like. Okay, so I gotta like do it this way because I don't want to explode anymore. Okay. Oh. There's not a lot of juice in here. All right. So every element has a different signature. So let's do some cool ones. So this is calcium. Oh, there's no thingy. Great. Okay, not calcium. Oh, here's another calcium. Ready? I think it's out of juice. Okay, we'll have to use the other one. Gotta use butane instead. All right, so. Okay, how best to do this so I and others don't get hurt. Okay, ready? All right, calcium. Lights? Okay, yep. There we go. So that's calcium. So the blue is just from the flame, from the combustion, but here's the color calcium. There you go. See it? Okay, that's calcium. Now let's do another interesting one. Let's do strontium. There's another 2A element. You can't see it at all? Help out, people. Go, 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 go. Oh, is it the projector? Okay. Yeah. Ah, ha, 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 ha. All right. Here's strontium. Oh, there we go. Okay, there we go. It's red. Here, let me do calcium again. There we go. So what we're just seeing is all the light from the line spectrum, but it's all, you don't see the discrete lines. Everything's kind of like muddled together. All right, let's do, okay, let's do our 1+, 1A cation. So here's lithium. There we go. Ooh, everyone loves lithium. Yes. Yes. Okay, there's lithium. Here is sodium. Who here has a gas stove? You ever like let your pasta water like boil over and then you like see the flames and they lick up and they become all yellow? That's what you're seeing, like any of the salt in the water. Once it goes down in the flame, it becomes all yellow. Yes. Okay. So there's calcium, potassium. Oh, no, sorry. That was sodium. Now it's potassium. Let's see how this one looks. It looks similar to sodium, I think. Yeah. All right. There's potassium. And I already did lithium. I did sodium. Here's copper. Has anyone, whenever I cut copper tubing, I always like to keep it because I like to put them in fires. Because this is what it looks like a copper pipe when you throw it into fire. Do you see the slight, come on, go. It looked green. Do you see the green in it, kind of? There we go. Okay. Did you see the green, kind of? Yeah, so when you throw copper pipe into fire, that's what happens. Okay, and the last one here is boric acid. This one's like a true green, or it should be. Oh, nice green color. All right, so those are all the colors. Yeah, so those are the line spectra of our different elements. Okay. So hopefully that was interesting. Yes. Oh, that's not. What? You like the lights off? Well, then I can't, I have to teach. I still have to teach. Okay. Yeah, no, you want this. You want this. Okay. All right. So that's why all that matters. All right. So what we were looking at, were we looking at electrons, the light that we were seeing, the different colors, was that from electrons being promoted or falling down? The electron, was it being promoted or falling down? Where light was being emitted. It requires energy to go up a ladder, right? So it was the fire dance here that was promoting the electron, but the light being emitted was from the electron falling back down to a more stable energy state. All right, so that's how all of that comes together. Okay, so we left off talking about wave behavior of electrons. We left off, talking about wave characteristics of light and it behaving like a photon, so a particle. So it's not much of a difference to say, oh, Well, if light can be a wave and a particle, then maybe particles can be waves, like electrons. And that's what de Broglie said with de Broglie, his wavelength equation, that all matter in our universe that's traveling at some velocity actually has a de Broglie wavelength. And so from the equation, you can see the trends here. As the mass of something decreases, really, really small items or objects actually have pretty large de Broglie wavelengths. Small objects like electrons. Electrons, because they're so small, have appreciable wavelengths that we can actually measure. And this is the whole basis of quantum mechanics. When things are really, really itty bitty small, they have important wave characteristics we need to consider. For really big objects, their de Broglie wavelengths are really tiny, where it doesn't actually matter or affect our classical, physics calculations, classical, like, Newtonian physics. It doesn't affect our calculations because its wavelength is so small. It's only for really small objects like atoms and electrons where it matters. And so just believe me, electrons can act like waves, right? So electrons acting like waves, we see scenarios and phenomena where electrons are acting like waves. A wave property is diffraction. Waves diffract, where we have constructive interference, where we have increases in amplitude of our wave properties, and then we have deconstructive interference, where when you add them up, their waves cancel. So when we subject electrons to diffraction, they also diffract. They undergo this wave characteristic. So it took a while longer for us to actually see this phenomena. We always thought of electrons as particles. This technique, this is scanning electron microscopy, is a technique that we do at this very university. We're utilizing the wave characteristics of electrons. All right, so Heisenberg's uncertainty principle. We're getting deeper into quantum mechanics here, where things are really small. In the quantum world, when things are really, really small, it's hard to know everything about the electron all the time. So it's not like classical physics. In classical physics, you kick a football across the room. Go Chiefs. Yes, I won. I didn't stay up for it though. I got bored. And then at the very end, it was good. Whatever. You kick a football across the room. You can know everything about that football at every moment of time. You know its mass, you know its velocity, you know its angle, its position in space. You know everything about that football. But the thing is, that football is big. So you can use classical physics to describe it. Electrons, they're so small, you can't know everything about it with great precision. So yeah, in the quantum world, it is impossible to know two measured values precisely at the same time. And those two values are something are position and velocity typically. So this brings us to Heisenberg's uncertainty principle. So he got another Nobel Prize that basically said the uncertainty in a electron's position times its uncertainty in that electron's momentum has to be greater than some universal minima that is related to Planck's constant here that we've seen in other types of equations. So it essentially says that if we know with great precision one measured value, we have to have a large uncertainty in the other measured value, and same thing vice versa. I like to use the analogy, like, you ever watch NASCAR maybe, or the premise of what NASCAR is, car go round thing real fast, right? Goes real fast. Okay, so your car is going real fast around the track, all right? Let's say you take a picture of the car going around the track. If you take the take a picture of the car, you now know what in that picture, you measured what about that car. It's position. You basically collapse the wave function. Now you know the position of the car at that moment of time. In that picture, you know its position, but do you know anything about how fast it was going? No, you lost all that information once you took that picture. That's what we call collapsing the wave function, where now you've measured one for certainty. Or we can do it the opposite way, right? That car is going real fast around the track. You take the radar gun, right, and you track it. It zips by, and it tells you, oh, it's going 150 miles per hour. But once you take that measurement 150 miles per hour, its velocity, it's way gone. So you lost all that information about its position. And so that would be gone once you take that measurement. So you see how you can know one, but not the other. So the idea here is that you can have, some uncertainty in both measurements and still obey Heisenberg's uncertainty principle. So Bohr's model actually violates the uncertainty principle because we know for certain in his model where that electron is, that we're saying, oh, it's orbiting. So we know too much about the position. The real model for our atomic structure is Schrodinger's model, using the Schrodinger equation and solving the Schrodinger equation. This does not violate the uncertainty principle because we're giving the electron a wider space to occupy. That's where our orbital pictures come from. So if I say like an SPD orbital and those kind of ring a bell, those orbital shapes are just telling you, oh, this is the probability of finding an electron with that energy in this space, in this spherical space, versus in a dumbbell shape. So we're basically giving more uncertainty to position for this electron, but we know for certain its energy. So we're collapsing the wave function for energy, but we have a lot of uncertainty with position. And that's where our orbital shapes come from. So then our memes, the idea that the electron is hard to locate, all right, that we have to, instead of saying, oh, this electron lives right here on that atom, we can't do that. We have to give larger orbital shapes to represent probability of finding an electron. So this idea is basically where Schrodinger's cat comes from, where have you heard about the thing, Schrodinger's cat, but do you truly understand it? Maybe, I don't know. Let's see if you do. So it's related to an electron. What Schrodinger said was, it was a thought experiment. He actually never killed a cat. All right. He had this mysterious box. All right. He had this mysterious box where he put a cat in it, and then he put a radioactive substance in it that would kill the cat if it went off. But the thing is that the radioactive substance, it was just random if it would go off or not, right? So he put both of those in the box and taped it up so you couldn't see inside. So one, he doesn't know anything about the radioactive substance, whether it'll go off or not. But he does know if it does go off, it'll kill the cat. But if it doesn't go off, then the cat stays alive. So the idea that both of those objects are in that box and he doesn't know whether the radioactive substance went off or not. If you're looking at the box, we have to deduce that both the cat is both dead and alive at the same time until we open the box. When we open the box, we take the measurement, we collapse the wave function, and we know whether the cat is dead or alive at that moment. Once we open the box, we essentially, we change it by taking that measurement. And that's the whole basis of the Schrodinger's cat. A lot of jokes come from it, but I don't think it's kind of an interesting thought, philosophical idea that because we don't know whether the poison went off or not, the cat has to be both dead and alive before we open the box, is basically where that comes from. So I don't know if I ruined the joke for you, but that's basically, what this is. And it's all based upon Heisenberg's uncertainty principle. All right. So does that clarify what this is? All right. And how it's related to electrons also. Okay. All right. So with that idea, we can't know where the electron is with precision. So instead, we use orbital shapes to just show a probability map of where we could find an electron given a certain amount of energy. This all comes back to Heisenberg's uncertainty principle. So when I show these orbital shapes, do these kind of look familiar to some of you? No? Okay. All right. So you got to study these. We have s orbitals, they're spherical. P, they're dumbbell shaped. D orbitals, they're these butterfly shapes. We won't talk about f orbitals. So S, P, and D are the ones that we care about. These shapes come from solving the Schrodinger equation, which we won't do. But I want to show it to you anyway, so you can impress your friends at the bar. So Schrodinger basically said, okay, an electron is a wave. It needs a proper wave function. So he built it. He basically used a wave function to say, hey, the total energy of my system, of my electron, is equal to all of the forces on that particle. So you can think potential energy plus the wave function involved with its movement and mass, so kinetic energy. So essentially he's just stating the total internal energy of the system, but using a new type of math, quantum mechanics. You don't have to know this equation. I just want you to, if this shows up on Big Bang Theory and your friends are like, what the heck is that? And you see upside down triangles and you can say, oh, that's the Schrodinger equation. And then you sound real smart. Okay, we never solve this. What's important is out of this equation, when we do solve it, when really smart people solve it, what we get out are our quantum numbers. So this is the solution to the Schrodinger equation. And what we get out of it is that there's only a certain number of solutions to this equation, to this wave function, that makes it valid. And this is where our quantum numbers come from solving all of that stuff that you don't need to know. But what comes out of it are quantum numbers. What you do need to know are what these quantum numbers represent. It represents the energy. Oh, I deleted some stuff, the energy or size of the orbital that your electron can reside, and it represents the shape of the orbital that that electron can reside. That's what the Schrodinger equation tells us, those orbital shapes. That's where it comes from, but we mere mortals don't actually have to solve it. All right. So we're going to look into, okay, what do these different numbers mean? There's 4 of them. So let's just go in order what they mean. The first quantum number is the principal quantum number. This is our n value. We're looking for just integer values right here. So this first principal quantum number identifies the shell the electron is in. N values start at 1 and they count up just using integer values. All right. So typically the trends that we see with n values, as the size of your orbital increases, n increases. So here's an example of a 1s orbital where 1 is the n value, s is the shape. A 2s orbital will be different. So essentially we're saying, oh, the probability of finding a 1s electron is in this smaller region versus the probability of finding a 2s electron is in a bigger region, right? That there's just a bigger region to find that higher energy electron. Okay, so that's the first one, the principal quantum number. That's typically related to size or energy, so that's n. The next one we'll talk about is shape. That is our L quantum number, and then orientation, that's m sub L. And so I'll go on to the next slides. So the next quantum number is our L quantum number. So this is our subshell. It tells us our shape. So here are the rules. In a certain n value, there's only certain valid L values. So for certain principal quantum numbers, there's only some allowed shapes or subshells. And so here's the rule. For a certain value of n, the only allowed L values are all of the integers between 0 and n minus 1. So for example, if we had an energy level principal quantum number of n equals 4, the possible L values would be 0, 1, 2, or 3. Those are the only valid ones. So each of those numbers actually represents a shape. Because an L of 1, I don't know, it doesn't really conjure up a shape. So each of these numbers are represented by a certain shape and letter designation. So an L of 0 always means an s orbital. An s orbital is completely spherical. So you should associate those two in your head. I guess it is something to memorize. But what this L value actually is the number of angular nodes on the shape. And so an s orbital has 0. That's what the number means, is the number of angular nodes. You might be thinking, what is an angular node? The analogy I use in 1210 is if these orbitals were balloon animals, it's how many times you need to twist the balloon to get that shape. So if you start with a balloon and you want a spherical shape, how many times do you twist the balloon? 0. So that's why L is 0. If I wanted a dumbbell shape, that's a p orbital. How many times do I have to twist the balloon? Once. So that's why L is 1. What if I wanted a butterfly shape? So this one's a little bit harder. You twist it twice. Once you have the first twist, if you like bend it and then twist it again, then you can get a butterfly shape. And so that's why L is 2 or D a d orbital. So those numbers actually have significance. It's the number of angular nodes in the shape. So yeah, L of 1 is S, 0. L of 0 is S, L of 1 is P, and L of 2 is D. We probably won't talk about F orbitals here. All right, so those are our common shapes. So if we had an electron that had an N of 3 and an L of 1, we would say that electron was in a 3p subshell. 3 is the N value, L is 1, so we designate that as a P. All right. And of course, in our N equals 3, other subshells do exist with different L values. So if we named this subshell, that's N equals 5, L equals 2, that N equals 5 is would be this 5 orbital, and L of 2 is a subshell of a D. So this would be a 5D orbital. All right. Why is there no such thing as a 2D subshell? Yeah, so we're kind of doing this, but a little bit backwards. So a 2D implies that N equals 2 in this case. A D subshell is an L value of what? D is, just look up here, look up there. It's L of 2. Is that combination allowed? No. I like to think the first D subshell has to be 3D. That's the first one. That is the only allowed N and L combination that you can have. Luckily, all this stuff is kind of on the periodic table and it can help you. All right, so those are our L values. It tells us the shape of our orbitals. The next important one here is our magnetic quantum number. This describes the orientation of each of the orbitals that we have. So for a specific subshell, a certain shape, there's certain orientations we can put that subshell and it be in a unique orientation. So I like to predict we have a sphere, a perfect sphere. If you rotated that sphere in like an electric or magnetic field, it would not change the forces on that sphere at all. It's perfectly spherical. So basically there can only be one orientation of an s orbital. So when L is 0, meaning an s orbital, the only M sub L we can have is 0. And so I like to think, oh, there's only one orientation for an s orbital. We can only have one box. And I'll show you what I mean in a little bit. So for an L equals 1, this is a p orbital. So it's a dumbbell, all right, a dumbbell. All right, so there's many ways we can orient a dumbbell in an XYZ coordinate system and it be unique. And so we can align the lobes on the x-axis, we can align it on the y-axis, or align it on the z-axis. And so there are unique ways we can align it. So our p orbitals actually have 3 different unique orientations. So how we can get it, I forgot to mention the rule here, depending on our L value, all of the quantum numbers of M sub L we can have for that subshell are all the integer values between negative L and positive L. And so all those integers. So you see here, the only s orbital we can have is a M sub L 0 orientation, but for a p orbital, we can have -1, 0, +1. So those are 3 different orientations. So for a d orbital where L is 2, we can have -2, -1, 0, +1, +2. So total, those are 5 boxes we can have. 1, 2, 3, 4, 5 boxes that we can put electrons in. And each of those boxes represents a certain orientation within our D subshell. Oh, I needed to write that. Okay. -2, -1, 0, +1, +2. All right. So in general, the number of orbitals or the number of boxes in a subshell is 2 times the L value, so the shape, +1. And so it works for all of these. So how many orbitals, how many boxes would you draw for a 2s subshell? How many orientations of a 2s? So the value we're looking at is the shape. So since S implies an L value of 0, we're only going to draw one box. So there's only one orbital there. So just 2s is going to have one box, one different orientation. That 2 doesn't mean anything in terms of boxes. It just tells us how big the orbital is or what its energy is. So the 2 value, the principal quantum number, doesn't tell us anything. What about a 3s subshell? How many orbitals are in there? How many boxes are you going to draw? Also one again, yes, just one, because again, it's an s orbital. So a 3s also going to just have one box. What about a 2p? How many boxes are you going to draw? Three boxes. Yes, all p orbitals have 3 different orientations. A 3d subshell, 3d, 5. Yes, so d implies an L of 2. So there's 5 different boxes here. It's still this exact, one more box, exact same thing, same things we did up here. All right, and then I have a mistake down here. Do you want to do 4F or 4P? We'll do 4F. 4F. So how many orbitals will be in an F orbital? 7. Yes, 7. Yeah, those are a lot. 1, 2, 3, 4, 5, 6, 7. Nope, one more. Need one more. Yep, 7. Those are all the different orientations. All right, and it comes from how we get the ML value. It's all the integer values between plus and minus. The L value, those are the number of boxes that we can have within that subshell. And I like to think about it in terms of boxes because we can only put 2 electrons in one box. That's what I like to think about it. And that's, I think, the last quantum number. We did M sub L, now we're doing M sub S. This is the 4th quantum number. This is what allows us to put 2 electrons in one box. So here I have the different energy levels or the different orbitals based upon their energies for a hydrogen atom. Here's 1s. See how there's only one box? Here's 2s, there's also one box. 2p, there's 3 boxes. Each of those boxes can hold 2 electrons. So the spin of the electron is its ms quantum number, that s implying spin. So the only way we can put 2 electrons in a box is if one spins up and one spins down. So we give those values, those quantum numbers, as +1/2 or -1/2. Those are the only ways we can get 2 electrons in a box. Right. Okay. And so opposite spin. And so we use plus and -1/2. So that's our last quantum number. So we built our boxes. They have different energies based upon their principal quantum numbers, different shapes based upon their L values, different number of boxes also, depending on their orientations along the XYZ coordinate system. And then the last one, spin, to get 2 electrons in a box. So this is important because there's some guidelines we have to follow to fill electrons in these orbitals when talking about certain atoms. Is that what we're going to talk about next? Nope. In the next slide we will. Pauli's exclusion principle, particularly where the rule is we cannot have 2 electrons with all same 4 quantum numbers, and that's why we have to have this last quantum number, spin quantum number, because we can't have 2 spin up electrons. Then all 4 quantum numbers would be the same, and then we would violate Pauli's exclusion principle. So I'll show examples in the next slides. Okay, so let's do a comprehensive problem here. What are the possible values for all 3 quantum numbers for an n=4 subshell? So there's a method, a strategy here. I basically am asking you how many boxes, how many orbitals are there in an n=4 subshell? So I like to think about, okay, if n=4, what are the possible L values I can have? What are the rules for L? It's all the integers from 0 to n-1. So L can equal 0. It can equal 1. It can equal 2. Tell me when to stop. It can equal 3. Stop. Okay, good. Yeah, so those are all my possible L values. All of those L values have shape letter designations, S, P, D, and F. Just for fun, you can write that, right? So those are all the shapes. With each of those shapes, we can have different orientations too. So in order to get the ML values, our orbital orientations, we need to look at these L values separately. All right, so I'm gonna do the L=0 first. If L=0, what are my possible ML values I can have there? Just 0, that's it. Because remember the rule for M sub L, it's all the values between -L to +L. And so since it's already 0, that's all you can have. So that's L=0. So now let's do L=1. What are our possible M sub L values we can have? -1, 0, positive 1. So that is 3 different orientations we can have. So I like to draw boxes because I understand putting electrons in boxes. So that L equals 0, that's an s orbital. That's just one box because there's only one ML combination there. How many boxes do I write for this L equals 1? 3. So 3 boxes. There are my, what are these? These are my 4 p orbitals. That's 4s. Okay. Next, we just keep going in order. So L equals 2. My possible M sub L's are -2, -1, 0, +1, +2. So how many boxes? There are 5. Yes, 1, 2, 3, 4, 5 different ML combinations. So 1, 2, 3, 4, 5. These are my 4 d orbitals. All right. Did I take care of all my shapes? Nope. Got to do one more. Got to do the L equals 3. So M sub L equals -3, -2, -1, 0, +1, +2, or +3. So I draw a total of 7 boxes. 1, 2, 3, 4, 5, 6. I think that's 7. I don't know. Those are my 4 F orbitals. Good. All right. So those are all the possible values of the quantum numbers. So how I could ask this question is, how many total orbitals are there in an n equals 4 shell? So if I asked how many orbitals in n equals 4, you would count how many boxes there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 different orbitals in an n equals 4. All right. I can ask this question a little bit differently. All right. So those are the boxes. Each box is an orbital. What if I asked how many electrons can possess an n equals 4 quantum number? We already did all the hard work. We already got that there's 16 orbitals. How many electrons can we put in a box? 2. So how many electrons can we fit in those boxes? 32. Yeah, so it's 16 times 2 electrons in each box or each orbital. All right, and that gives us 32 or whatever. Oh, do I have the answer down there? Yeah, I already do. Okay, great. All right, so hopefully you see the pattern. What if I had an n equals 5? How many orbitals would be an n equals 5? 25, yes it is. But you can prove it to yourself and actually do it. Where you would just add another row. You would just do L equals 4. And if you do that and add up all the boxes, you'll get to 25. And then if I ask the question, okay, how many electrons can fit in an n equals 7 subshell? Or not, sorry, n equals 7 shell. First, I would ask myself how many orbitals, how many boxes are in n equals 7, and what would you say? What's 7 squared? 49, but then 2 electrons in a box, so whatever 49 is times 2. So 98. Yes. Yes. So that's how you would approach that. Or you could do it all, right? And actually draw out the boxes, but I don't feel like doing that. Okay. So those are all the different boxes we can have. All right, so let's talk about placing electrons in those boxes. There's some rules we have to follow, but they're kind of intuitive, okay? When given a certain number of electrons, we always want to fill the lowest energy boxes first, right? So if I give you a sodium atom, there's only 11 electrons on there. So you're going to put your first electrons in the lowest possible place first, and then start building up. That's Aufbau's principle. So you always fill, for example, 1s before 2s, before 2p, all right? Because that's the order of the energy that they exist in. The next rule is Pauli's exclusion principle I mentioned before, is that the reason is here is that no 2 electrons can have the same 4 quantum numbers. That's why we need that last spin quantum number. So we can only put 2 electrons in a box if they're spinning opposite. We can't have 2 in the same box spinning the same way. Okay. All right. So we can never violate that. And then the last one, Hund's rule, this one's a little bit different. For degenerate orbitals, degenerate means all the same energy. So these are like s orbitals and d orbitals. We want to follow this rule. we want to maximize the spin of our electrons before we start doubling up and spin pairing our electrons. All right, so the reason is because of energy. That this configuration, if I needed to put 3 electrons in a p orbital, I want to spread out the spin, have them all kind of dancing the same way, in the same orientation. This is the most stable right there. Okay. While if I, congregated my electrons, I have opposite spin here and I don't maximize spin, this is actually a greater energy. Atoms are always trying to minimize their energy. This is not stable, so do not write electron configurations that way. And also this one is not stable either. All of these electrons are in their own box, but one is spinning the opposite way. So this also is not energetically favorable. So do not write it that way as well. We want to draw our electrons in the most stable arrangement. All right. So those are all of our quantum numbers. How did we get our quantum numbers? How did we get those? They come from. We just solved this Schrodinger equation. That's it. That's it. But that's no, easy feat. So hopefully I can show you all the information you need to memorize these quantum numbers is on the periodic table, right? So there's a lot of information here. Once you see and start building electron configurations off the periodic table, it won't be so bad, I promise. All right, so homework is due for the first part of chapter 6, right? Okay, all right. So the last part of this chapter is we'll now do electron configurations and periodic trends. And so I'm just going to get us to valence electrons, and then we'll jump ahead to chapter 7 and then come back here. But this homework set will be due next Monday. I will probably hold off other homework sets until we're finished with chapter 6 and 7. Okay, so big idea. Each of these orbital shapes and orientations is a box on our energy level diagram. How many electrons can we put in a box? 2. So there's a way that we follow Aufbau's principle, Hund's rule, Pauli's exclusion principle when placing electrons. So to place electrons, we just look at the atom. So here is the energy level diagram for hydrogen. How many electrons does hydrogen have? 1 electron. Where are we going to put that 1 electron? In the bottom. We're going to put it in the bottom, right? So I'm going to put that electron right there. That's it. That is the electron configuration of hydrogen. There's only 1 electron. So we can write and tell a reader exactly where that electron is. We can say, oh, that electron is in a 1s orbital, right? Because that's 1s. That's the lowest energy orbital. And there's 1 electron. So that is the electron configuration for hydrogen, telling the reader exactly where to find an electron. Okay, so that's for hydrogen. Now let's do all the other elements. Okay, so here's how we do the electron configuration for multi-electron atoms. So the problem is when we solved the Schrodinger equation earlier, we only did it for hydrogen. So you and I, us mortals, we can solve the Schrodinger equation for hydrogen. Once we get past hydrogen, once we get to helium, there's 2 electrons floating around there, right? And it complicates things. And we can no longer solve the Schrodinger equation on paper. We actually have to give it and hand it off to computers, supercomputers, to do it for us. So here is the supercomputer solution to all of these multi-electron systems. So everything other than a hydrogen atom. See how the energy levels start to split a little bit, but we can still follow our rules. If we know what this looks like, we always, follow Aufbau's principle, fill from the bottom up. So it shouldn't be a big deal. So let's write the electron configuration for a sodium atom. Yep, okay, we look at the periodic table. How many electrons do we place? 11, yeah, so let's do that. Where do my first electrons go? 1s, yeah, so 1, 2. Now where did I put my next ones? 2s, so 3, 4. And then I put the next one in the p orbital, 2p, so 5. But where do I put my next one? Do I put it in the same box or the next box? next box. So 5, 6, 7, but because I have more to place, I can now start doubling up on them because there's nowhere else for them to go. So how many am I at? 7, 8, 9, 10. And then that 11th electron goes into a 3s orbital. So that's it. Right, so that was us following Aufbau's principle and Hund's rule there. And so we can write out the electron configuration here, telling the reader exactly where to find electrons, starting from the bottom up. So a 1s orbital, there are 2 electrons in there. What about our 2s orbital? How many electrons are in there, in that box? 2. How many electrons are in my p orbital? 2p. 6, and then there is 1 electron in that 3s. All right. Okay, we can write the shorthand for this. If you look at the periodic table, if you look for the nearest noble gas, I like to think you can use shorthand noble gas electron configuration notation, where you use neon as like a checkpoint, So I can replace all of these electrons with neon in brackets and just say 3s1. That's another way to do it. So I can replace all of those numbers, those electrons, those 10 electrons that come from neon with neon in brackets. That's just the lazy way to do it. So you can use any one of the noble gases as a checkpoint to take care of a bunch of electrons for you. So you want to pick the nearest one that's lighter in that case. Okay, so it was quite easy to see where to place electrons when I had this diagram for you. But the thing is I'll never give you that diagram. But we don't have to memorize this diagram. Everything we need to know is on the periodic table. All right. So you can use the periodic table as a resource. This is why it's shaped this way. Here is our S block. Here is our P block. And then here is our D block. I like to memorize that hydrogen starts at 1s. And then if you work your way down, hydrogen's 1s, lithium's 2s, sodium's 3s. This element that's right here, this is boron. Boron starts at 2p. There's no such thing as a 1p. Okay, so p start at 2p. Boron starts at 2p, so that means aluminum right underneath is 3p, gallium is 4p, indium is 5p. And then finally right here, these are my D block elements. These are my D block elements. So scandium starts at 3D. Oh, that's scandium. Scandium. That starts at 3D. Because the way we kind of approach this, given a substance like oxygen, for example, if we locate it on the periodic table, where's oxygen? It's right here. It's right here on the periodic table. All we have to do is just start at hydrogen and fill up our electrons with those respective orbitals and make our way up to oxygen. So if we wanted to write the full electron configuration for oxygen, start at hydrogen and you go 1s2 because we want to fill these 2 electrons, those 1s electrons. Then you move on to the next part of the periodic table, lithium, beryllium. So you fill your 2s2 because lithium starts at 2s. Then you work your way over to boron. Boron starts at what orbital? 2p. So 2p, do I fill it up the whole way? No. How many electrons should I put in my p orbital? Just 4, because I just need to hop over 4 to get to oxygen. That's it. So the periodic table literally tells you everything. I can write the shorthand here where I can, for oxygen, I can use a save point at helium, and that replaces that 1s2, those 2 electrons. I know it's not much of a shortcut, but when our elements get really big, doing shorthand is nice. All right, so there's our shorthand. Okay, let's do potassium now. So where is that? It's right here on the periodic table. So same idea, start at hydrogen, work your way towards potassium, knowing where the different SP and D blocks start. That's how I do it. So potassium, 1s2, 2s2, 2p. I'm working my way all the way to the noble gas. So I'm going to fill up that p orbital the whole way. What orbital comes next after 2p? 3s. Yes, if you look at this chart that I have all messy, 3s. Do I fill it up the whole way? 3s? Yes, you do. Yes, you do. Yeah. We're not there yet because potassium has a bunch of electrons, like 19. We haven't placed 19 electrons yet. So after 3s, what's the next orbital? 3p. Yes. Why not 3d? Why not 3d? That's weird. So let's keep going. So 3p, do we fill up the 3p the whole way? Yes, we do. Okay. And then what comes next? Now we get to our 4s. And how many electrons do we put in there? 1. Yes. After 4s, then we get to 3d. So the d orbitals are kind of placed in this weird energy compared to other energy levels with these multi-atom systems. But as long as you follow the rules on the periodic table, having 3d after 4s that's perfectly fine. All right, because our 3d orbitals are actually a little higher in energy when they're empty compared to 4s. So this is absolutely okay. All right, and so if we wanted to do the shorthand here, it would be, what's our closest noble gas? Argon. Yeah, so it'd be argon, 4s1. Isn't that nicer to write? Yes, it's much nicer to write when we start having larger atoms. Okay, what about zinc? Let's do zinc. So let's just do the shorthand for zinc. So zinc on our periodic table is right here. Let's do a different color right here. All right, so we want to make our way to that location on the periodic table. So where is my closest noble gas? You have to work your way backwards. It is argon again. So writing argon in brackets, that actually takes care of 18 electrons for us. Yay. So if we're at argon and we go to potassium next, this is where it gets tricky when you use shorthand, because we have to know what orbital is that potassium period at. It's an s orbital, but which one is it? Is it 1s, 2s, 3s? It's 4s. Yeah, so you have to kind of work your way back from the beginning to see, okay, hydrogen's 1, lithium's 2, sodium's 3, so potassium is 4s. Do we fill it up the whole way? Yes. How many electrons do we put in that 4s? 2, and then 3d is next. How many electrons do we put in there? 10. Yes, that'll bring us all the way to zinc. All right, let's do germanium next. It's, just 2 electrons over. And so the trick is, we can actually use all of our work from our zinc example, 4s2, 3d10, but if germanium is 2 more electrons over, we're just gonna add 2 more electrons. But in this case, they're going into 4p orbitals, which is kind of tricky here, because once we get to zinc and we jump over to our p block, remember the numbering system, it's 2p, 3p, 4p. So we want to put 2 electrons in that 4p. All right, so those are electron configurations. Do practice these. I should be able to give you any element, and all you need is the periodic table to get the electron configuration. We'll mainly be worrying about the shorthand because we can still see valence electrons, and that's what's important to us. All right, some anomalous, it's like 50-50 whether I can pronounce that word, electron configuration. So these are ones that don't follow our trend as much. They're just exceptions to our rules, but it's quite straightforward to see here. If we look, okay, on our periodic table, some of the exceptions that we see are in our D block elements that basically, if we have a completely filled, we get an extra amount of stability if we can completely fill a D shell or exactly fill a subshell. So for example, for chromium, if we wanted to write the electron configuration for chromium, you would expect, based upon where it is, you would put 2 electrons in the s orbital, 4 electrons in the d orbital. But the thing is that there are 5 different orientations in a d subshell. So we would actually get some energy back if we put in one of the s electrons in the d subshell. So then we have 2 half-filled subshells. It's kind of like a game of poker, and you're like rearranging your hand to get like two better groups of cards rather than just like stacking it all in one grouping, if that makes sense. So what we see for chromium is this exception, that one of those electrons jumps to the D subshell, so we have two half-filled subshells, and that's much more stable. So if I like drew this out, all right, 1, 2, 3, 4, 5, this arrangement, so having one electron, everything's all spinning up, that is much more stable than having the arrangement where you have two spinning this way, all right, completely filled S subshell, and only 4, so just a partially filled D. That's not super stable. Yeah.
How do we like know which ones are like this, like ones where this exception applies? Like, is it like a list to memorize?
Yes. Yeah. So chromium's one, and then it's big brother molybdenum also does it, but not tungsten. So chromium and molybdenum will do it. We'll do this, where one will jump ship. Yes. So just those two for that type. Then the other one is copper, but it's for the same reason. If you tried to write the electron configuration for copper, you would get 4s2, 3d9. So essentially you filled up the d orbital 90% of the way. So why don't we just like consolidate our pizza into one pizza box and put one electron into the D subshell so that it's completely full. So we get that energy stability back. So it's for the same reason copper does the same thing. So for copper, instead of finding S2D9, you actually find S1D10 instead. Right. So basically for the same reason, because completely filling that D subshell is much more stable than filling just a tiny S subshell and like partially filling this huge D subshell. So you see it for copper, you also see it for silver and gold. They are in the same group, right? So it's just those two. Those are the only two that you need to know it. Most of the other ones that we'll ask are completely predictable off the periodic table. Right. So yes, do memorize those ones. So I just remember chromium and copper, all the copper groups, and chromium and molybdenum. We'll do the jumping ship thing. Okay, so let's look at some questions. I think it's like pretty simple and straightforward to ask a student, like, tell me the electron configuration of this, right? It requires you to know Aufbau's principle, Hund's rule, all that stuff. I think what's harder is to look at diagrams and determine, you know, is it right or wrong? I feel like that's quite an easy question, but to look at, let's look at the wrong answers and explain why it's wrong and what principle does it violate. I think that's a harder type of question here. So here are a bunch of different diagrams. Which diagram violates Pauli's exclusion principle? So we have to remember what that is. What's Pauli's exclusion principle? 4 quantum numbers, right? Every electron needs to have 4 different quantum numbers. So which one violates Pauli's? What do we think? Why did we need Pauli's exclusion principle? That one is what described our magnetic spin quantum number. It's why we had to put an electron spin up and spin down. So the only diagram here that violates that is B. Why? Like you might look at this and be like, yeah, B is wrong. B is definitely wrong, but why is it wrong? It's because both of the electrons are spinning up. We can't have that. That violates Pauli's exclusion principle. That's wrong. So how could we change the electrons in this one to make it right? What quantum number would we have to change to make it correct? Just think, how would you move the electrons to make it right? You would change the spin, right? And then ask yourself, spin is related to what quantum number? M sub S. So you would change the MS quantum number to make it right. Okay, how about Aufbau's principle? Which one violates Aufbau's? That principle is building up. We fill from the bottom up. So which diagram violates that? Yes. C, yes, because we have this vacant spot. We should have put this electron there, right? Because we didn't fill from the bottom up. Okay, Hund's rule. Which one violates Hund's rule? You can say it. You can be brave. Hund's rule is the rule that maximizes spin. So which one does not maximize spin? A. Yes, because this electron, right, the highest energy electrons, we want to spread those out, all spinning in the same direction. So this one I need to flip and move to a different orbital. Are there any diagrams that are, someone might ask, oh, what about E? Is E correct? E is actually correct. It is correct. Yes, it is correct. No, so you guys, you're reading left to right. You think that like if we were placing electrons, right, I have to put them left to right. I actually don't have to. So once I fill these lower energy levels, yes, I have to fill them like that. But when I put the next electron in, our human brains want to put it in the leftmost orientation. We also want to make it spin up for some reason, but it's equally energetically allowed to have that next electron spin down. It doesn't matter. It doesn't matter. Or I could put that next electron in the middle. It doesn't matter. Okay, that all of these are the same energy. I could put the electron there, there, there. I could put it in, you know, upside down. It's all right. But it's when I place the next electron, it matters. So, you know, once I place an electron here, there is an energetically favorable spot to put the next electron. I have to put it either in this box or this box where we maximize spin. But could I put it in this box but spin down? No, I can't do that because that does not maximize spin. And I also cannot put them in the same box like that. All right, so there we go. Okay, so these two are correct. These two are correct. So D is actually, what element is that? Boron, I think. And then this one has 2 electrons, and that's what, carbon? Okay. But that's like an easier type of question. I just show you the diagram. Those are the elements. Okay, all right. So some other questions here. How many unpaired electrons does a nitrogen atom have? So we might want to write out the electron configuration. So I'm going to do shorthand here. So helium, 2s2, 2p3. So we might need to write out the actual electron, the orbital diagram. So I'll just draw all of it. So here's our 1s orbital. Here's our 2s orbital. And then how many boxes do I draw for my 2p orbital? 3 boxes, yes, to fit all 6 electrons if I could. So 2p, there we go. So now I need to place the electrons. There are 2 electrons in the 1s. That's what's represented by the helium subshell. I actually didn't have to write that out. 2s is also completely filled. Now there's 3 electrons in the 2p. We want to make sure we maximize our spin to follow Hund's rule. All right. So based upon this diagram, did I place all my electrons? Yes, those are 7 electrons. So how many unpaired electrons are there? Oh, whoops. Okay. Yes. Thank you. Okay, perfect. All right. So how many unpaired are there based upon my picture? Only 3. Yes. There's a lot of places to go wrong here. All right. If you don't draw the electrons correctly within your orbital diagram, you might, like if you don't follow Hund's rule, you might have different pairings. We can't just count total number of electrons either. Yes, nitrogen has a total of 7 electrons, but some of them are paired. Drawing the diagram helps you there. All right, so let's identify all of the neutral elements that contain 2 unpaired electrons in their 5p subshell. So I like to draw it this way. Okay, so if I have a 5p subshell, how can I have 2 unpaired electrons? If I put 1, 2 electrons like that, there we go. 2 unpaired electrons in our 5p. So that means that this element is 5p2. Can you, just based upon that, determine what element that has to be? What element does that have to be? 5p, 2 electrons in it. Carbon, wait, 2, 3, 4, 5. Which one is it? Tin, yes, it is SN. Yes, SN has 2 5p electrons. Very good. Did I miss one? I said all neutral elements with 2 unpaired electrons. Okay, how about this? Okay, okay, we have 2 5p electrons. What if I just start adding more electrons? That's 3 unpaired electrons. But what if I add another electron? Now how many unpaired I have? Yeah, see, Yeah, I tricked you, didn't I? Yeah, so there's another way we can get 2 unpaired electrons, and that's having 4 electrons in the 5p. All right, and so then what element is that? What element's that? So this is 5p4. So this is tellurium. Based upon the periodic table, we're making the assumption that all of the rest of the electrons before it are completely filled. So we just care about what's on the outside, right? These are actually called the valence electrons, the ones that are highest in energy. These are the electrons we care about. Valence electrons explain why elements behave the way they do. These are the outermost electrons, all right? So typically, valence electrons are the electrons highest in energy. Typically, they're the highest N value most of the time, right? So these are like usually the electrons that are after, you know, your noble gas shortcut thing. Also, these are the electrons that are most likely to participate in chemical reactions. That's why we care about them. And so being able to count them is important here. And there's some tricks. The thing is that we don't technically need to write the electron configuration every time we need to like figure out how many valence electrons are in nitrogen. We don't actually have to do that. We don't have to write the full electron configuration. That's annoying. All the information we need is on the periodic table. So here are the rules for main group elements. So like our S and P block elements. The number of valence electrons on those elements is its group number. That's it. So all of my group 1A elements, if you wrote out their electron configuration, they would all have just 1 electron in an s orbital after that noble gas configuration. That's why they all have 1 valence electron. Or for example, nitrogen. So we just did nitrogen. How many valence electrons are on nitrogen based upon its group number? 5. Yes, but let's look at its electron configuration too. The highest energy electrons, how many highest energy electrons are there on nitrogen? 5. And again, it comes from its group number. So main group elements, super easy. It's just their group number. Where things get weird are D block metals. Okay, so I like to describe this as early D block metals, meaning D block metals that are kind of early in the group. All right, so like D1 all the way to about D5. So these metals, you include the your S electrons. For those lighter D block elements, you do include the S electrons. But for later in the D block, once you start adding a lot of D electrons, you start stabilizing that whole subshell, and it becomes harder to remove subsequent electrons. So these electrons, you typically do not include, what I have in green, you don't include their S electrons. So for example, scantium, and the way we know this is through reactivity. Scantium, right, if you look at scantium, that is 4s2 3d1. So you might think, oh, there's only 2 valence electrons there. But the thing is we sometimes see scantium 3, sometimes we see scantium 1. And so that tells us that there are actually 3 valence electrons on scantium. So we can see, oh, we include those S and D electrons. Yeah. Yes, D6 also kind of. Iron also has multiple oxidation states. I promise you, I will not ask one in the very middle, right? Okay. So manganese, for example, manganese, it's 1, 2, 3, 4, 5, it's D5. We actually see manganese 7+, implying that it loses all of its S electrons and its D electrons. So that tells us, oh, there's 7 valence electrons on manganese by the reactivity. But once we start getting heavier over here, we start only seeing 2+ cations. So that's why we see, okay, like cobalt, nickel, copper, zinc, all of those typically don't exceed +2 cations because their D electrons are too energetically stable by that point. So that's what I call the later D block elements. All right, so there we go. Okay, so those are valence electrons. So let's go through these. let's go through these, and then next class we'll skip ahead to chapter 7, Lewis structures. So let's get these valence electrons, because we need this skill for doing Lewis structures in the next chapter. So I'm going to give you the choice. I want you to tell me the number of valence electrons for all of these elements. You can either do so by writing out the full electron configuration for all of them, or you can just use the periodic table. Which one do you want to use? The periodic table. So let's do that. Okay, sodium. Remember the rules. It's usually the group number. So sodium, it's in group 1A, so it has 1 valence electron. Also, when we think about sodium as a cation, what is it usually? Actually, what is it always? +1. It always loses that 1 valence electron, and that's it. All right, so we never see a sodium +2. That doesn't exist. Okay, what about sulfur? How many valence electrons? Based upon where it is. So right there, 6 valence electrons, because it's in group 6A. What about scandium? Right here. It's 3 valence electrons, because basically we used our argon, what did I say? Our argon like save point, and then we added 3 more electrons. So we can just remove those 3 valence electrons to get back to our save point. So this is 3 valence electrons. We want to include the 4s and the 3d. What about zinc though? Once we get all the way to zinc, it's a heavier D block element, so we've completely filled that D shell. So zinc actually only has 2 valence electrons because of the 4s. And this is tricky. This one's tricky, right? Because sometimes D electrons count, sometimes they don't. So in zinc, they don't because it's so stable. All right, bromine. How many valence? 7. What? 7. Group 7. I love main group because it's just, it's group. All right, oxygen. 6. Carbon. 4. Silicon. Also 4 because it's still group 4. Aluminum. 3. Yep, it's right here and right here on the periodic table. Should I be highlighting these? So there's, yellow on yellow. Aluminum is right there. Calcium, right? 2. Okay, great. Vanadium. Right there. Yeah, this one's tough. So it's like, do we include the D electrons or not? Because it's 4s2, 3d5. We do include those D electrons. So it's 5 valence electrons. I know because vanadium 5+ exists. Vanadium 5+ exists. So vanadium can lose 5 electrons. Lead. 4, yep, because it's main group. Silver. This one's actually tricky. Silver is one of our anomalous electron configurations. It's right here on the periodic table. We would write it 5s2, 4d9, but does it actually exist that way? No, one of those electrons jump ships and consolidates that D shell. So it's 5s1, 4d10. So based upon this, how many valence electrons are on silver? Just 1, yeah, because it'll just lose that 5s electron. Is it likely it'll lose those D electrons? No, because it's all super filled, right? So it's going to keep those. Okay, manganese. I already told you this one, it's 7. So that's one where it can lose all of its D, all of its s orbitals or s electrons. Manganese, or sorry, magnesium. Sorry, magnesium. Just 2, yep, because group 2A, neon. 8, very good. Yeah, even though it's a noble gas, it still has outermost electrons, valence electrons. Noble gases are group 8, and so 8 here is just the outermost electrons, though they're not typically lost in this case, but it still has valence. All right, so we'll get to Lewis structures. So have that in your back pocket for Thursday. We will do Lewis structures, chapter 7 stuff then. I'm gonna post the exam results when I get to my office, because everyone has taken the exam now, unless you don't want them to, or you don't care.